Hi everyone, I'm Xingyu. But there are a lot of Xingyus in PLI, including one of the speakers today. So I'm becoming Jupiter, like the plan. Yeah, so I'm currently a third year PhD applied by Professor Sanjeev Arora. I work on like theory for language models, basically. Uh, yeah, so that's about me. And today, welcome to our like first PLI lunch seminar this academic year. We'll be hosting this seminar like nearly every Thursday at this exact time at this location. Yeah, so you're also welcome to please attend all the following talks. So the first speaker we're having today is Xingyu Fu with a PLI postdoc. So here's a brief intro. So Xingyu is a postdoc at PLI. She earned her PhD from UPenn, where she was advised by Professor Dan Roth. Her research focused on multimodal generated models at the intersection between vision and language models, natural language. Xingyu won Best Paper Award at the CB&W workshop at CSharp 2024. She received OpenAI's Research Access Program Reward and the JP Morgan Fellowship. She previously also interned at Microsoft and AWS. Yeah. So let's have a
thank you so much, another Xingyu from Xingyu. Hi everyone, I'm Xingyu, and I don't have nothing. So like I am just starting with PLI. Oh, is this better? Okay. So like for those who don't know me, I am starting at PLI as a postdoc here. This is from August, and yeah, as you can see everyone here. I'll just get started. But like feel free to stop me if you have any questions. So multimodal models are really popular nowadays. They're taking up all the headlines on the news and getting a lot of discussions. However, as a suspicious person, I always wonder, like, are they always this good as advertised? And the work I want to present today all started from a very simple idea, which is like, can human really identify like AI generated videos? Like, are they destined to be able to fool people? So why don't we just try to answer this question together by looking at this very short video, and then let me know your answer after watching.
What are we trying to answer?
Can you identify if this is an AI generated video or a real video? Like telling me a reason. Yeah.
It's AI because the people are disappearing.
Yes, yes. I'm just showing the annotation here. Like we found that despite of the video quality, humans can identify the AI generators with very concrete and and by the way, this is Sarch video, so it's one of the best quality ones. So the next question is, can AI identify AI generated videos? Like, can we have AI police for AI? So this is an example I tried by myself. Just when making the slide, I just asked Gemini model because I saw stories from OpenAI and I don't want any data overlap. So I asked, is this a real video or an AI generated video, and asked it to give me a reason. And Gemini, it's actually the latest Gemini 2.5 Flash one, told me like it's real. Unfortunately, this is real. It gives me like a really long analysis on why this is real, like based on the physics movement and a lot of different details.
But it was trained a year ago, so it's
the latest release.
I know, but still.
Oh yeah. The data. That I agree. So I want to introduce Deep Trace Reward today, which is basically a reward benchmark that aimed for teach AI to identify AI videos with grounded evidence. This is just a little bit detail on how we did the annotation. Basically, it is like using like a hybrid way of doing the annotation, because like we use language model to generate the prompts for the video, and then we do manual filtering on the prompts, and then we use machine to automatically generate the video, but now we also do manually filtering on the videos. And we did use a really good platform for annotation, which is called Label Box. And given a video, we have a bunch of experts that they can like select inside the video on which part is incorrect, like has a problem, and then provide a reason for it. As in the explanation part, feel right natural language. And we will collect the bounding box for the areas that had a mistake. And it also comes with timestamps, like start and end. And here are some like interesting examples from the deep trace rewards. This was like a goalkeeper, like in a soccer game kind of video. And then the type of problem here is the goalkeeper like gradually splits into two body and still collecting the two body. During this process, we call it object splitting. Another reverse version of the problem we identified. This is like two odors like moving in the water and gradually they merge into one. So like object merging. These are like previous ones are like more simpler ones. There are also harder ones. For example, this one here. The problem with this is like if you look at the car behind the people, you'll see that it's like slowly having some change in the shape, which it shouldn't be. Like during this process, the yellow car. So like we kind of try to call it background distortion, which is like as the pedestrian is walking across the street in the video, the pedestrian side is moving, but the car in the background undergoes like an unexpected change. It should remain like the shape most of the time. Another like harder problem to detect is like object trajectory. And this is a little bit hard to identify. Like this was a video, and then it was like basically saying that a train should go from here to there, and the camera is still, so that these things should stay there with the same shape and same location, but it gradually comes forward to the camera. So like that's we call it object trajectory. Unexpected move. Yes.
Yeah. So do you guys do any labeling on like psychological problems? Like for example, here you have the, the lights that go like this, but the railway is actually going like perpendicular to it instead of in between them.
Yeah.
Do you guys catch that as well? Or?
We are more course complete compared to that. We're more like if we're more focused on moving things, especially inside the video. It shouldn't be still, it should be something moving, and then we're more like identifying what's like moving unexpectedly during this process.
Yeah, I guess there could be like a lot of things that physically make sense,
Yeah.
but I guess like lack of common sense, and that seems to be, I don't know how good.
Yeah. I think I would say every problem is a combination between perception and reason. If you recall the Sarch problem, some people disappearing, it will make sense if that's an entrance on the stair. And it's only mistake if it's stair instead of an entrance of the elevator. Yeah, great question, I think. We put everything together and present this deep trace reward bench. It contains like 33 unique fake videos, 43, 34 like expert annotated labels. Each label comes with bounded region and temporal timestamps. Like for training purposes, we also include 3318 unique real videos. How much does this cost? 10 graduate students. Several months of effort. This is like an analysis of the data set. Basically, it has like 9 major categories of the problems that I just introduced in the examples, like object splitting, merging, background distortion kind of. And we did collect, yeah.
Oh, sorry. I'm guessing there are also cases where the video is AI generated, but it's like there's no mistakes. What do you do with those cases?
Yeah. So like we found that with moving, so like it depends on what the video is about. If it's like more still videos, then it's a lot of times don't have many obvious mistakes that human can identify. But if it's like moving things with moving objects, let's say people, animals, like the boats, vehicles kind of thing, it will almost always make a mistake. And also there is another extreme, which is it makes too many mistakes. Like everything is wrong inside the video. We actually like dispose those kind of things because too many mistakes. So like that's exactly why we only use videos from those different models because these are more like high quality than compared to other ones. And I'm just putting the statistics here to show that we did use videos with high resolutions and we don't include videos that are too short, like below 5 seconds. Yeah, this is
What's fake length?
like if you remember when we annotated the fake reasons, it comes with start, second, and end second.
Or
So like that's
that box?
yeah, that's always not so short compared to the whole video. Another fancy figure to show the whole thing. So like the next step is reward modeling. How do we realize this goal to teach AI to identify AI with real reasons? And the way we do it is using like video language models, basically given a video. So the way this kind of models work is it turns the video into multiple frames. And then with the question, try to predict the answer in language, in natural language. And the answer should have explanations and spatial temporal boundaries. Basically, this is an example of what the model is really using. Like this is the prompt, decide whether the video is AI generated or real by like detecting unnatural parts and then give the bounding box, give the reason, give the starting time. And this is the example like answer, which is like, yes, this video is AI generated. It happens at which bounding box area, starting at which second. This was the Sarch one. So, and the reason is because like after carefully observing some people there, a single something different. Before we show the results, another question is like evaluation metric. How do we evaluate this? So it is it is in two categories. One is classification, which is like very normal, like it can classify fake versus real video correctly. And we did show fake accuracy, which is like the accuracy for fake videos, and the real accuracy, which is accuracy for real videos. Because some models can like think all the videos are real, and some think videos are for like better illustration. And another line of evaluation is the reasoning part, like whether they can answer like the fake versus real reasoning correctly. And we do like have score for explanation because we ask it to generate like the explanation in language and we use language model as a judge. And we do include like bounding box, there's a B here. Bounding box IOU and distance, which is basically the overlap between the predicted bounding box and the annotated bounding box, the overlap area, and the distance between the centers of the two bounding boxes. Finally, we have time distance, which is the distance between the predicted starting second versus the annotated starting second. They're all normalized. So this is a huge table. You don't need to like look at it all at the same time. But like, yeah, so our first takeaway is our 7B reward model can achieve GPT and Gemini level performance. By the way, I forgot to say the overall metric is basically a combined metric considering both the classification and reasoning. So we call it overall. And we can see that especially our model based on the video llama 3, it can achieve like 30 something better over than the GPT models and 40 something over the Gemini kind.
So video llama 3 is not better than 2.5 VL because it's not.
It was also trained on some video data. So my thinking is maybe a little bit over time. Also, like, it's different in like how they compress the video. So video llama 3 is more efficient. So. And then the second takeaway is that classification is easy, but telling the reason is hard. If you see the performance on the classification accuracy versus the overall scores on reasoning. Oh, by the way, so some score is the higher the better, some score is lower the better, depending on like the average. You can see that the reasoning part is usually always harder to achieve good results compared to the classification.
So how do you do the train validation split?
Train what?
Train validation split, like, because you mentioned like you use data to tune the one model and the other one just to evaluate here. Is it just like,
We spend two on the validation. We just train on the train set.
yeah, but like how you split the train set, like it's just like
Oh,
idea.
8-1-1, something
I
like
see.
that, by ratio.
But there is a possibility that you have better performance on the video one just because like they have this, like the fake has a different distribution than the real one. For example, the fake ones are more artificial and
Oh, you mean these two?
no, just like the image data itself.
Oh, you're saying the model has been trained on image related tasks and then they are all real images.
Yeah.
So you're expecting the models to behave better on real videos?
Yeah.
Oh, we can take a look. That's real accuracy, basically the accuracy on real videos, and then that's a fake accuracy on fake videos. I think for those like released models, it is the trend that you said. That the real ones have higher performance than the fake ones. Maybe because they've seen the real ones. But in our training spot, especially the video llama 3, I feel like they're playing. Yeah, good point. And so like the third takeaway is temporal grounding is much harder than spatial grounding. Comparing the time results versus like the bounding box results. Like for time, if it reaches 100, basically means it's the starting predicted starting second is so far away from the annotated starting second. And we think it might be because like the model in nature turns a video into multiple frames. So like it loses some control. Yeah, this is another like result analysis back to the 9 major categories that we introduced previously. We wanted to show like whether different categories will like behave differently for the trained reward model. And we see that like most of them almost like have similar results, I would say. A natural language actually provides like a great space for supervision. And one observation from that category table radar figure is that like object shape centered problems are easier for model to detect, which is like making sense because like a lot of vision based models trained for object shape related purposes. That's pretty much everything. That's features reward. We're released on seeing archive probably this month and for everyone's interest. Thank you so much.
So next up, we have our second speaker, which is Gabriel Sarch for Gabe. Yeah, so here's a brief bio. Gabriel Sarch is also a postdoc fellow in PLI. He is studying multimodal agents capable of complex visual reasoning and decision making. Gabriel completed his PhD at Carnegie Mellon University in the machine learning department and neuroscience institute as an NSF graduate research fellow. He was advised by Dr. Katrina Rekiataki and Professor Michael Park. His work has been published in leading venues including Europe, CPR, CPJCL, and Nature Communications. And he also held research positions at Microsoft Research and Utori AM. So let's have a warm welcome to Gabe.
Thank you. Thanks for the introduction. I'm also a new postdoc, so I'd love to chat with any of you after the talks. And yeah, so I'm very excited to chat with you about some of my new research on grounded reinforcement learning for visual reasoning. So we've seen the success of large language models on a variety of different tasks. They can do things like creative writing. They have a lot of world knowledge, code generation, and so on and so forth. So a natural question to ask is what's next? And I would argue that the next thing are these multimodal AI agents. So web agents that can automate computer tasks for us, wearable AI assistants that sit on the device, can see what we're seeing and help us do things in our environments, and robotics assistants that can do physical tasks for us in physical spaces. But if we actually look at the performance of frontier models on these type of multimodal tasks, they often fall well below human performance. So here on the left side, I'm showing you this multimodal web navigation benchmark, Visual Web Arena. Here, models get multimodal input, vision, and language, and they have to carry out tasks on live web pages. And you can see this big gap between human and models like GPT, Gemini, Qwen, and even the newer models. You still see a large gap here. And then even just general visual understanding in BQA tasks, you also see a large performance gap. Here I'm showing the blink benchmark, and the pink lines there are the human performance on these visual tasks. And in the middle are all the frontier models. Again, you see this gap, and again, models released today still have this kind of gap between human performance. And so what I would argue that is still missing from these multimodal models is being able to better reason through inputs when they're tasked with very challenging multimodal problems. And so if you consider, maybe I ask my model, my dishwasher's not working, can you help me figure out the reason? And I give it maybe some images and some information about my dishwasher. We essentially have two types of models to help us answer this question. We have these reactive models, which are just going to immediately output their best guess response. And so they're not really going to do any sort of planning, adapting, or active assessment of the information before giving an answer. And then we have these reasoning models, which are going to spend extra test time computation to go about deriving the answer before giving an answer. And so it's going to do more computation to plan, investigate, verify, weigh the options before returning an answer. And so you might define reasoning in different ways, but here I'm defining it as the process of allocating additional computation to infer the correct answer when it's not immediately apparent. And so if you think about this continuum of tasks, or maybe you have this x-axis on the left side, you have maybe easier tasks like object recognition, and on the right side, you have harder tasks like investigating a problem in your home. These reactive models are going to spend the same amount of computation regardless of the difficulty of the task. And what I think we really need are these reasoning models that will spend more computation for harder tasks. And one approach to this has been chain of thought prompting, where basically instead of having the model directly output the answer, you have it reason step by step before actually providing an answer. And so in domains like math, with especially larger parameter models, you see a big gap in performance between using chain of thought and reactive performance. So this is a while back on the GSM 8K, but this still holds true today. And even in visual tasks, this is the Sketchpad work where these authors, they allow the model to use Sketchpad in the chain of thought and have the model manipulate the image during chain of thought. And do this kind of visual chain of thought also improves performance over the more reactive version of the model on a variety of different visual tasks. Okay, so why is this chain of thought actually helping? So chain of thought is the reasoning process needed to derive the answer. So it's, again, like I mentioned earlier, spending extra test time compute to explore, verify, and refine its answer. So this allows it to generalize better than just predicting the answer because it's going through the process of actually deriving the answer. And another way to look at this is if you think about problems solvable by Boolean circuits of size t. If you have a constant size transformer, this transformer can solve it by generating order of t intermediate tokens. This was a result last year at ICLR. And so if you're just directly generating final answers, you either need a very huge depth in the model or it can't solve this type of problem. Okay, so this sort of chain of thought prompting is elicited through prompting. And so you need a lot of prompt engineering, but can we actually instill this type of reasoning in AI models through learning? And so we now have models like O1 and R1 that are trained with reinforcement learning, where you have the model sample different reasoning chains and you apply policy gradient updates. based on a verifiable reward signal. So if the chain of thought leads to the correct answer, you reinforce that chain of thought. And we've seen how this leads to more human-like reasoning, where the model does better step-by-step reasoning, verification, it'll backtrack when it's incorrect. And this type of RL on chain of thought has shown to improve performance significantly on math and coding reasoning. But what about visual reasoning? So there has been recent works applying this type of RL on chain of thought for vision language models. And so you do a very similar thing where given, let's say, an image and a question about the image, are the cutting boards below the bowls? You have the VLM sample different reasoning steps. The boards are near the edge of the counter. The bowls are higher up near the shelf, so the boards are positioned below the bowl. And then you have it output an answer. In this case, the model is correct, so it gets positive reward. And you have the model sample different reasoning chains, some leading to correct answers, some leading to incorrect answers. And you apply these policy gradient updates based on this reward signal. But actually just applying this type of reinforcement learning naively on base vision language models doesn't always lead to strong reasonings. So here I'm taking this Quen 2.5 BL model, which is a popular vision language model, and I'm asking it, how did the camera rotate between these two pools? And if you just prompt the model for chain of thought, what you often get is these very vague and ungrounded scene references. So it just kind of mentions some objects in the scene. It says, oh, the objects are in different positions, but it doesn't do a very fine-grained analysis of the objects in the scene to as it relates to the question. And so this often leads to incorrect answers. And if you do RL tuning on top of this model, on similar examples, this sort of abstract, ungrounded reasoning doesn't really get better.
Question?
Yep.
So my rule of thumb for RLBR is that the model already had the capability, but just less frequently. Like you have to sample 64 times, see the right answer.
I see.
Is that happening here or not? Because if not, then my rule of thumb would say that RLBR would not.
So if you sample the prompted chain of thought from the base model
64 times.
64 times.
Yeah.
So yeah, I think eventually, even with this kind of vague chain of thought, it may get the right answer, but it doesn't. That doesn't always generalize better when you're trying to get top one accuracy.
Oh, I see. Here it can just guess them. Yeah. So
Yeah. Right. And so yeah, so here RL tuning and I think to
sorry,
get
but I think sorry, my rule of thumb is that it has to have the right reasoning. That's when it'll improve. Yeah. Because you'll reinforce it.
I see. Yeah. So here, even what we observe is the reasoning is very ungrounded, abstract, and so it leads more often to the wrong answer because of this. And we ran a behavioral study on this model for a lot of different tasks of these complex spatial reasoning tasks, and we find is that this model often will only mention about 2 visual regions when it's reasoning about the image, which is much less than, let's say, a human would do when it's reasoning about these complex spatial tasks. And even worse, if we look at other behaviors in the chain of thought, like does it set visual subgoals? Does it do region verification in a fine-grained way? Does it backtrack when it's incorrect? We observe almost none of these behaviors before and after RL tuning. But actually humans do things very differently. We do much more iterative region level reasoning through eye gaze and visual attention. And so here's a eye gaze trace of a human looking at the scene. And so you can see how humans will iteratively look at and reason about different parts of the scene and kind of stitch it together. And actually Ullman in 1984 described this concept of visual routines where we use grounding to scaffold and form our reasoning into these decomposable spatially localized steps. And similarly, Ballard in 1987 described deictic codes where he described how we use fixations, pointing, gestures to really bind abstract variables to perceptual content during our reasoning process. And so all of this is to say that human attention isn't just about perception, it's really how we guide our reasoning. And so given that we found these VLMs are very abstract in their chain of thought, we hypothesized that having the model explicitly ground these reasoning steps in specific image regions will help it both see better and think better during the process. So if we consider standard chain of thought, it will just output these textual thinking steps and then an answer. We can now define what we'll call grounded chain of thought And here we have the model only reason about one part of the image and have it explicitly ground that in an XY coordinate in the image. And we have it iteratively at each step, reason about one part of the image and ground it in that XY coordinate. And it'll do this iteratively until finally it ends in a final answer. So how can we actually teach these VLMs this type of grounded thinking? So the first thing you might think to do is let's get humans to manually annotate this grounded chain of thought. So this is going to be slow, expensive, it's hard to scale. And so another idea you might think to do is to take a more proprietary teacher model and maybe distill from this model. But we also found that it's really hard to enforce this type of grounded thinking, even in these larger proprietary models. And if you ask it to generate this long chain of thought in one pass, even these large models often are very abstract. And so instead, what we're going to do is we're going to search over individual grounded reasoning steps where the model only outputs one reasoning step at a time in this tree search fashion. And then we're going to distill this into the VLM and run online RL to amplify this type of grounded reasoning that will lead to correct answers. So to go into more detail on this, we're going to run Monte Carlo tree search over individual reasoning steps. So for example, if we have an image here and a question, we prompt the model at each node to generate one reasoning step about one part of the image and an explicit XY coordinate about where it's reasoning about. And so each of these nodes in the tree correspond to only reasoning about one part of the image. And we can do this iteratively until some terminal nodes end in correct answers, indicated by the green there, some end in incorrect answers. And we actually found that running this procedure forward often leads to correct answers for these types of spatial reasoning tasks. And so now what we can do is we can linearize paths through this tree and create supervised data out of this. So for example, we can start at the root node where the input is. We can traverse down these reasoning steps until we end in a correct answer node. And then we can concatenate the text along this path to form some supervised fine-tuning data. So we can add this to our supervised fine-tuning set. And we can also add backtracking data in the same way. So we can traverse down a tree to an incorrect answer, explicitly backtrack, and then go down a correct path. So here we can get concatenate this, ending in a wrong answer, have it backtrack, and then go down the correct path there.
Sorry, how does it go? Know where to go?
So we explicitly add this data. So basically we say, we traverse down this path, we know it's an incorrect path. And then we say, wait, this is off, let me backtrack. And then we go to a previous node and then we go down this other path.
But the human is there's a feedback.
So we just concatenate the text generated by the model because each of these nodes have model generated text.
Yes.
And so we just concatenate it with some concatenated string that says, wait, this is off, and then the next concatenated text. I can show you what that looks like next. Yeah. So yeah, here's what this data looks like. And we find that we get very rich visually grounded behaviors from this iterative process. And so we get behaviors like sub-goal setting. It's good. The model says in a particular node, now I'm going to check this area grounded in a particular XY coordinate. Visual verification, I'm going to verify this visual feature. And here's where I'm going to verify this. And then we also have this backtracking data because we explicitly added. So here it went down a bad reasoning path. We add the string here. Let's try something else. And then we continue down the correct reasoning path.
What's the sibling?
Sorry?
What's the sibling?
This is the particular question. So this is an instruction to follow Candace person. And so it's trying to find in this page what button actually corresponds to that. So I think somewhere in here it mentions some sibling in the description. Yeah.
Okay, that's it.
Yeah.
Does it backtrack all the way to the very start? Because it looks like it's starting over again after.
We vary it. So it depends on where kind of the lowest step node where those two paths will intersect. And we can vary that depth. Yeah. Okay, so then we take this tree search, we're going on many examples, and we'll distill it into our VLM. And so this bias it towards this type of grounded behavior. And then on top of this, we're going to run online reinforcement learning to continue to refine this behavior after this norm starting. And our reward is going to be a combination of outcome accuracy reward, whether the model got it correct, and also a format reward to ensure that we maintain this type of grounded reasoning format. And we'll evaluate the model on spatial reasoning, web grounding, trying to find elements in web pages, live web navigation, and visual search. So answering questions about fine-grained details in an image. And so here on spatial reasoning, on the spatial aptitude.
Can I go to 2 seconds?
Mhm.
Yeah, just my question is about the trees, the trees search step. So every step you propose a step. That's by the 70 billion model.
Yeah, by the
And
larger
also
model.
the answer verification is also by 70.
The answer verification, it depends on the domain. Oftentimes we can do just string matching. If it outputs
basically
the
model proposed answer.
Yeah, so at each step, we prompt it to say you can either generate a reasoning step or you can generate an answer. Yep.
Can I ask a follow-up? Just like you're assuming you have a very good, I mean, to be fair, like you have a very great like 70B model providing like one structure, right? That kind of assume like you do have a expert that's providing very expensive like supervision, but in a scenario you don't have this kind of like supervision model, which is
So I think you can still use a smaller model. Because if you're only prompting it to, we didn't explicitly test this, but even like a 7B or 32B model, if you just prompt it to output one step, it will often follow that instruction. It's when you have to generate the full length chain of thought, it often will generate 1 or 2 steps and then an answer or something. Yeah, maybe I'll just move on real quick and then just go move right. So on this spatial reasoning benchmark, spatial aptitude, we find that over doing vanilla GRPO, so just doing GRPO directly on the base model directly, we can significantly improve using our method. And if let's say we start with this 3B model, so this is kind of the base performance. If we do this grounded tree search and then distill it into the model, we can significantly boost over the base model. And then continuing to do this online RL really refines the behavior. We get further boost there. And actually, if we remove the explicit grounding, so we do our same process just without it having explicit grounding in the reasoning, this also causes a drop in performance, indicating that having this explicit grounding really does help performance here.
it's the analog of the SFT phase in GRP.
Yes. Do you mean this step here?
Yes.
Yeah, exactly.
So your last part here still is SFT and GRPO, but just move on. So the final.
Exactly, yeah. So this is our same pipeline as this one. It's just without explicit grounding.
Still
We can also test our model on web grounding. So here, given a high resolution image, the model needs to localize a particular button on the page. And again, we can outperform the vanilla GRPO as well as a direct SFT baseline. These are apples to apples on the same data. And then on live web navigation, we can train on action prediction data, and then we can deploy our model on live web pages. Again, in this visual web arena where you get multimodal instructions, and we can outperform the previous state of the art for this parameter size, as well as the base model. And then for visual search, we can also have a multi-turn variant here where if the model really needs to see very fine-grained details in the image, we can give it some zoomed in feedback. So here, let's say each reasoning step has some text and a coordinate. We can then give it visual feedback of a crop around that coordinate at a higher resolution so that it can see what it wants to look at in a higher resolution. And so each step also gets this visual feedback until it ends in an answer. And doing this, we can beat the previous 7B VLM reasoner state of the art at the time, which was Nemo VL, and also the state of the art tool use pipeline, IBM Enhanced Zoom, as well as the base model that we fine-tune on top. And one reason that this sort of grounded reinforcement learning seems to improve performance is it also amplifies other useful cognitive behaviors. So we find that our model compared to directly doing RL on the base model or doing our full pipeline without grounding, explores more visual regions, just more visual sub-goal setting, more region verification, and also backtracks more often when it's incorrect. And then we also run a human evaluation to check how accurate our intermediate grounding actually is. And we find that humans rate our the XY coordinates as they relate to the reasoning steps about 75% accurate. And we also find that humans on average find that these grounded reasoning steps are helpful for understanding the thought process that the model took to reach its answer.
In terms of the backtracking on the previous slide, how much, like when you're doing the training in the initial SFT stage, how much backtracking do you add into the
About 15% of the SFT data is backtracking. If you add too much, it'll just always try to backtrack.
Yeah, I'm also curious like how extensive doing black color research in these cases compared
Yeah.
to I guess like living on.
Yeah, so it does take more time and it's more expensive because you're only prompting for one reasoning step at a time. So we do it async, so we have parallel processes and that seems to help, but compared to doing like best event or rejection sampling, it's much less efficient. But we find that it really does improve performance here. So we do some ablations there. So we end up using it. So here's some examples of our model. So this is a question, are the baskets next to the wooden spoon? And so the model will reason about the spoons, the baskets, other parts of the scene that might be relevant, and then finally give an answer. Here, it's a web navigation task, and the instructions, can you add this to cart if it's yellow? So the model reasons about the cart button. It then looks at the image detail, at the options, verifies this other image, and then back at the cart to land on the correct answer. Here, the task is, can you locate the calorie expenditure button? So it's going to iteratively reason about each one of these elements as it relates to the task to try to figure out which one is the most relevant, and then finally land on the correct answer. So we also still see some failure modes. One of them is overthinking. So here, it's a very simple task. Is there a part of the image? It's a recognition task. And our model will do a lot of thinking. It'll check many regions here to see if there's other pots in the image, verifying that there's only one pot, etc. And so while this doesn't always hurt performance, it wastes computation when it doesn't really need to do this type of thing. And then in general, while our model having this grounding reduces hallucinations, we find that hallucinations do still exist. So here is the plastic bag above the trash bin. It starts talking about a window in the scene when there's no window. Okay, so in conclusion, I've talked about how we should be teaching reasoning, not just the answers, emphasizing how to solve the problem over just what the problem should be. Supervision is hard, getting humans to annotate data is hard, and so we should be learning this reasoning with exploration and reinforcement learning. And visual grounding is an important part of reasoning. It can enhance reasoning, and it reduces hallucinations. So these are my collaborators on this recent work, and yeah, I would love to chat about this or any other related projects. My email and other info here.